Let's continue our discussion of the partial fraction decomposition integration method. So what we're trying to do is we're trying to integrate rational functions of the form p of x divided by q of x. And what we want to do for the very first step of our partial fraction decomposition is the following. If n, which was the degree of the numerator, is greater than m, we want to divide so that we get a quotient. Our quotient will be a polynomial. And a remainder. And let's call that remainder r of x. Okay. So what we're going to end up with is we're going to end up with a polynomial plus the remainder r of x divided by the divisor q of x. And really, it's this piece right here that we actually do the partial fraction decomposition on. So we do partial fraction decomposition on this piece right there. All right. So how does partial fraction decomposition work? Well, we have a theorem that says that all polynomials can be factored as a product of linear terms and irreducible quadratic terms. This word irreducible means, it can't be factored. All right. For example, something like x squared plus 1. It's a quadratic polynomial because the degree is 2. You can't factor it. Let's take a look at an example. Let's look at an example 3. This would be something we call factoring by grouping. Okay, what I could do is I could group the first two terms together. So I could write this as x cubed minus x squared. And then I can think of this as the second part is negative x minus plus 1 like this. And then what I could do is I could pull out a x squared from the first term, the first two terms. So I'll have an x squared, and I'll have a x minus 1 left over there. And then I could factor out a negative from the second two terms. So when I pull out a negative, that's going to give me a x minus 1 for those last two terms there. And then now you could see we have a common factor of x minus 1. So we can pull that guy out, and we're going to get x minus 1 times x squared minus 1. Now, when you look at this inside part, this is really a difference of two squares right here. So we know what a difference of two squares looks like. That's a squared minus b squared. That guy factors as a plus b, a minus b, right? So our polynomial is going to factor as x minus 1 times x plus 1 times x minus 1. So it's fully factored form. We could write this as x plus 1 times x minus 1 quantity squared. Okay, so let me just highlight that. That's our factored polynomial. Now, what we're really trying to do in partial fraction decomposition is we're really trying to factor this divisor q of x. So really, I want you to think of this polynomial as really a denominator for our partial fraction decomposition. So factoring is important to the partial fraction decomposition process. There's a few things I want to remind you of. The first thing is that we know that the linear factor x minus c is going to be a factor of p of x. If that's true, then when you plug in a c for x, you should get 0 coming out. Another way of saying this is we could say that, c is a root. We sometimes call that or a 0 of p of x. Okay. Another way of saying that is basically saying that x minus c is a factor of p of x. So, for example, if you had some polynomial like, I don't know, p of x equal to x cubed minus x squared minus 1, minus x plus 1, notice what happens if I plug a 1 in. If I plug a 1 in for x, I'm going to get 1 cubed minus 1 squared minus 1 plus 1. When you simplify that, you get 0. So this tells you that x minus 1 is a factor of p of x. Now, if you looked at our original example up here, we could definitely see that x minus 1 was a factor, right? In fact, it's a factor that's counted twice. But, let's say you didn't think of doing factoring by grouping. You could have done a quick check, noticed that x minus 1 was a factor, and then just use polynomial division to do example 3 instead. Okay. Another factoring trick I want to remind you of is we can really use substitution to help us factor. So let's say that we look at this polynomial x to the 4th plus 4x squared plus 3, right? What I can do is I can use a substitution to help me evaluate this. So what I could do is I could say, why don't we let w equal to x squared? When I do that, then my polynomial is going to become, well, let's first rewrite this as x squared quantity squared plus 4 times x squared plus 3. So when I make my substitution, that's going to become w squared plus 4 times w plus 3. And when I write it as a quadratic like that, I don't know, for me it's a little bit easier to factor. That's going to factor as w plus 3 times w plus 1. And then you can substitute back, right? So when we substitute back, we're going to get x squared plus 3 and x squared plus 1. So that would be our factored polynomial. Now, each of these two factors, these would be examples of irreducible quadratics. So some of you may have forgotten how I can determine whether a quadratic was irreducible or not. And in order to do that, I can use something called the discriminant. And that's used to determine if a quadratic polynomial is irreducible. Okay. So what is the discriminant? Well, do you remember when you have the quadratic formula, negative b plus or minus the square root of b squared minus 4ac divided by 2a? This formula gives you the zeros of a quadratic polynomial, and the discriminant is just this inside piece right here. This inside piece is the discriminant. So we know that if the discriminant b squared minus 4ac is less than 0, then this means that your polynomial is irreducible. So if we did a quick example, in our polynomial over here, the a is 1, the b is 2, and the c is 2. So if I calculate what b squared minus 4ac is, that's going to be equal to 2 squared minus 4 times 1 times 2. And that's going to give me negative 4. Negative 4 is less than 0. So this means x squared plus 2x plus 2 is irreducible. Okay. All right, everybody. We needed to talk about this factoring stuff before we can talk about partial fraction decomposition for real. Take care.